A lot of people have been talking about herd immunity as a strategy, and the R naught value as the number of people that an infected person will infect. And those are just two falsehoods. I think it's kind of interesting. We've been in this pandemic now for months. And the truth is, I think most of us have remained mainly uninformed, uneducated about it. We've learned 1,000 different numbers at one point or another that basically just added to the noise and didn't really give us an understanding. It's kind of like knowing the ideal gas constant without knowing the ideal gas law. We don't really know what to do with any of this information. It doesn't really provide any context. So I thought I would put together this little video because I'm just tired of it. And I'll link some videos that I actually put up for my students last semester when I was teaching computational methods. In any case, basically all of this stuff has to do with the SIR model. And basically the way to think about this is that it is the normal model that's used mathematically to try and figure out how an infectious disease propagates through a population. And I think the easiest way to think about it is kind of like as a chemical reaction. So we have A goes to B goes to C in terms of these molecules. Well, instead of having these molecules, now we have individuals that are in bins, so to speak. Susceptible individuals go to infected, and then they go to recovered. And once they're in this recovered or removed bin, they're immune, so they don't ever go back into the susceptible bin, even though that will eventually happen. Immunity goes away naturally over a period of time, but not usually within a certain season. And so this is a pretty good model. And it's really this recovery bin that makes it possible for us to talk about this flattening of the curve, this percentage, so to speak, of the infected population going down. It goes down because people are moved out of this infected bin into the recovered bin, and not just back into the susceptible bin where they'll be reinfected, but they're really considered in the model as recovered. And this was exactly what flattening the curve was all about in the very beginning. In the SIR model, once you've non-dimensionalized it, there's basically two parameters that are involved. There's R naught and there's epsilon. R naught is very simple. It's the characteristic recovery time, so about how long would I have to watch for someone to recover, over the characteristic infection time. How long would I have to watch this situation occur to see infection appreciably occur so that I could measure it? Especially and really appropriately when community spread is working, because you can see that in these infected versus time plots, the reality is that the number of infected people goes down, and so the only way that ever occurs is if the number of people that an infected person will infect also goes down. So R naught doesn't simply mean the number of people that every infected person will ever infect. If that were the case, it'd just simply be exponential growth forever, and that's absolutely not what we see ever. This picture right here, I'm also plotting with epsilon. And epsilon is the percentage of the population that's initially infected. And so in this case, I've taken 1% of the population, or really this should be fraction of the population. So this is 1% of the population that is initially infected. And that's the case for every one of these, but I have plotted them for different R naught values. So you can imagine if the R naught value is big, that means there's a long recovery time and a relatively short time required for infection. And in that case, we get, say, an R naught of 5. So it's 5 times longer for recovery than it is to cause infection. And we get this high peak, and around 50% of the population was ever infected at one time, and then it decays down to 0. And as R naught goes down, that would mean that the recovery time, in comparison to the infection time, the recovery time is going down in comparison to the infection time, or the infection time is going up in comparison to the recovery time. In that case, we have smaller and smaller R naught values, and this peak decreases, and it also spreads out in time. And here we've plotted things in terms of the recovery time. So this would be 6 recovery times worth of time. This would be 4 recovery times worth of time, and so forth. And so that's what the R naught value is, and we can see that changing the R naught value changes this spread. And this was what it was supposed to be, 2 weeks to slow the spread kind of thing. I think that was a disaster of a campaign in terms of its veracity. I don't think that we're still in the process of really thinking about spreading this out in order to slow it down. But this was the initial idea. The thing that's so important to understand is that the R0 value doesn't just change this peak or the time that it takes for the situation to resolve in terms of no infected individuals. If you were to also plot the percentage of people that are in the susceptible bin, you see something really interesting. For a high R0 value, the number of people that are in the susceptible bin goes down to practically 0%. But if the R0 value is kept pretty small, say around 2, look what happens. Once we've reached equilibrium, about 20% of the population remain susceptible precisely because they were never infected. And this is what we mean when we talk about herd immunity. Herd immunity is not a strategy. It is a fact about the SIR model and all of these compartmentalization models. Herd immunity just simply speaks to the fact that eventually, once the pandemic has extinguished, or the epidemic has extinguished, a certain percentage of the population will not have been infected. And it can be quite large if the R0 value is relatively small. In fact, if you were to plot the percentage of the final percent of the population that was never infected as a function of R0 here, so just this last, so to speak, data point as a function of R0, what you see is that for an R0 around 5, almost everybody's infected. But it goes down. As R0 goes down, this guy goes down. And so when we've reached an R0 of about 2, about 20% of the population can be safe. That means they don't have to get a vaccine because maybe they can't. There are people who have suppressed immune systems that their immune system won't work. You can't give them a vaccine and then develop antibodies. It won't work that way. So in this case, what we've done is we've allowed 20% of the population to basically be shielded by the rest of us, basically having acquired normal immunity. And that's what's meant by herd immunity. It's just a fact. It's not a strategy. In fact, by spreading things out and by, so to speak, flattening the curve, we've been pushing this R0 value artificially towards a smaller number that brings us to something more and more like herd immunity. Of course, it's going to pop right back up again because this R0 value really is being artificially suppressed right now. But let's take a look at some alternatives before we go in terms of what we've been doing. So the first is that we've been testing a lot. And the problem with the tests that we've been using is not that they're not good, it's that they're oversensitive, especially the way that sometimes they've been used. And they can actually detect the virus's previous presence even after a person has recovered for a long period of time, in fact. And what that means is that if you were to plot the SIR model here, and here I've plotted it for an R0 of 3, an initial percentage of the population of 1%, and I've assumed that the PCR test could detect the virus up to 3 recovery times after someone has recovered. And in that case, what you would see is the SIR model would look something like this. The number of susceptible people would drop down to a very small number at the end. This is what we call our herd immunity effect. The number of recovered people will start at 0 and then pop up to that final value around, it looks like 90% or over 90% of the people have recovered. And then we have the infected pool that first goes up and then it goes right back down again. But what we've also plotted here is the percent, or so to speak, the fraction of the population that could at any moment be tested and then have a positive PCR test. And you can see that it's huge. It's a huge number. It has nothing to do with this number, in fact, in terms of its order of magnitude even. It's much, much bigger. And so what that means is that we're really talking about a testing policy that doesn't give us the best insight into who's infected, who's infectious, because it's not tight enough in terms of its focus on the actual infected. It can count people who've already been really, recovered for quite some time. But the last thing to recognize that's kind of a hopeful thing is that really vaccines are a huge game changer in all of this. So what would happen if initially we were just able to vaccinate 20% of the population? What would that do? It would really change the dynamics of the problem entirely. So take a look. For an R0 of 3, if we had a vaccine of 20%, look what happens to this herd immunity effect. We've gone from this number right here to a number that's significantly better. So maybe 10% of the population here is actually uninfected, and the virus has extinguished itself. What if we could get 50% of the population to have this vaccine, or to have been previously infected and so be immune? If that's the case, the dynamics are totally different. We have a much smaller infectious kind of peak, but we have almost 20% of the population very likely can be shielded and be safe even if they don't ever receive a vaccine, because some people can't. And I think that that's really an important takeaway, because what we're trying to do with this vaccine is not just try and make sure that everyone takes it. That's crazy. What we're trying to do is change the game. We're trying to change the dynamics of the system. And really what we've done here by allowing this vaccine to create herd immunity for us, by this mechanism of immunity, what we've allowed is for this percentage of people that can be never infected to be really high. We've effectively dropped this R naught value from 3 to 2 by this vaccine. And I think that's really, for me at least, I think these are really important concepts, because when we really talk about all of these numbers that get passed around, IFR, CFR, the HIT, all of these numbers, they're valuable in some ways, but unless you have this background and they have kind of a framework to fit these numbers into, to understand what they mean, it's not useful. And we're just arguing over nonsense. And I think a great example of that kind of nonsense is talking about herd immunity as a strategy. It is not. That has nothing to do with a strategy. Herd immunity is a fact. It is a feature of the dynamical system that describes how viral infection propagates through a population. And obviously this is a very rinky-dink model, but it's the best one that we have. And really what it comes down to is they basically make R not a function of time to get it to be better. It's still a well-mixed model. It's it's not really, it's in need of a lot of help in terms of parameter fitting to get that R naught right, especially if it's a function of time. But the end of the day is that if we didn't understand what flattening the curve meant 7 months ago, talking about herd immunity right now like it's a magic idea is really detrimental to the entire scientific education of our population in order to really make good choices as far as what are we really trying to do in terms of making sure that we can open up our communities in a way that is responsible, but at the same time so that we haven't actually created a worse long-term effect with the shutdown. And I think this is really important for us to move forward and not have simple argumentation basically in echo chambers where people are encouraging just kind of sloganeering rather than thought. So R naught, really simple, characteristic recovery time over the characteristic infection time. We basically drove it down earlier by making this characteristic infection time longer by separating using social distancing, but that was artificial and it won't work forever. And it's definitely having an effect, a cost in lives. And then the last thing we had, this epsilon, was the percentage of the population initially infected. And lastly, we introduced one more parameter by allowing for the vaccine to really affect who would be affected. And we saw that in the end, we're still achieving this herd immunity. So don't let people make that a bad word. That's insanity. That's like pretending that the ideal gas constant is a bad word. It's just a feature of this particular model, and we need to be able to use it and not be shamed by people who really should know better.